Hello everyone. Okay, diving into Unit 2, starting with topic 2.1, which is types of chemical bonds. And so there are three main types, and if you remember from general chemistry and honors chemistry, the two of those three that we talked about the most were ionic bonds and covalent bonds. Okay? So determining the type of chemical bonds. Now, the main way that we decide what type of chemical bond is occurring is when we're looking at the types of atoms involved in the bond. So if we have a bond between a metal atom and another metal atom, then we would call this a metallic bond. Okay. Now, if we have a bond between a metal atom and a non-metal atom, this would be an ionic bond. And then our final type would be between a non-metal atom and a non-metal atom, and these are covalent bonds. Now, covalent bonds can either be polar covalent or non-polar covalent, but more on that in just a moment. Reminder, because it's been a minute, if we look at our periodic table, and when you're in class next time, I want you to look at the big periodic table that I have up on the wall. And you'll notice that this staircase line on my big periodic table is kind of been bolded, right? It makes it easier that we can see this line, okay? And there's a reason why we've done that, and that's because in general, to the left of this line, these are our metal atoms, and to the right of this line, these are our non-metal atoms. Now, there are elements that are touching this line, not all of them, but a good chunk of these ones that are like directly against the flat edge of this staircase line, and those are metalloids, that they have characteristics of both metals and non-metals. And then there's one exception that I can think of outside of those metalloids, and that is hydrogen. Even though hydrogen is to the left of the staircase where the metals reside, hydrogen is in fact a non-metal. But then all these guys over here, these are non-metals, okay? So if I were to quickly ask you what type of bond would occur between a lithium atom and a chlorine atoms, we would say, okay, well, lithium is a metal and chlorine is a non-metal, so that's likely an ionic bond that's happening between them. So here's what happens with these different types of bonds. With an ionic bond, the non-metal atoms have such higher electronegativity. So these non-metals, they have big electronegativity, and these metal atoms have such low ionization energy. So reminder, electronegativity is the affinity, the ability that an atom has to take electrons from other atoms. So when they have higher electronegativity, that means that they're more likely to grab electrons from other atoms. Now, ionization energy is the energy it takes to remove an electron. So if we got an atom that it's pretty easy to remove an electron, it doesn't take a lot of energy to do that, and then you have another atom next to it that is likely to take that electron, well, then that's what occurs. We have this neutral sodium and this neutral chlorine, but the chlorine is going to take away an electron, one or more electrons, from that sodium. In this case, it's just going to be one, and we're going to form a cation and an anion, because this lost an electron and this one gained an electron. Now, this gaining and losing of electrons is not actually the bond. The bond occurs after the atoms gain and lose, because now we've become a positively charged ion and a negatively charged ion. And we know that whenever there's a positive or a negative, then there is an attraction between those things, and that's what the ionic bond is. It's an attraction between those ions. Okay, so that's an ionic bond. Now, with a covalent bond, it's between two nonmetals. And like we said with the ionic, nonmetals have higher electronegativity. They're both trying to steal electrons from other atoms. But another important thing to know, especially for covalent bonding, is they also both have high ionization energy. So something happens here. Now imagine that my two hands are the nuclei of these two nonmetals. So here's a nonmetal, here's a nonmetal. And imagine that we have, oh look, Jesus is always the answer. I didn't know that was the pen I was holding. So imagine this pen is the electrons, okay? And so this atom is trying to pull on the electrons because it has high electronegativity, and this atom's trying to pull on the electrons because it's high electronegativity. And so they're both pulling on these electrons, and neither of them really want to let go of these electrons either. And so we get this tug of war. We like to say that covalent bonds are when atoms share electrons, but really, does this look like sharing to you? Maybe it's like reluctantly sharing. It's more of a tug of war that neither one is winning. But see how these electrons physically, like they hold these atoms together. This mutual attraction that they have for the electrons, that is what the bond is. That is binding them together. That's what a covalent bond is. Okay. Now, metallic bonds, on the other hand, are metals. And we know that metals, not only do they have low ionization energy, they're not really holding on to their electrons really strongly. They also have low electronegativity. They're not readily grabbing the electrons of other atoms. So if we go back to this analogy, if these are the two metal atoms and there's electrons between them, neither one is terribly interested in those electrons. It's like, this is more of a true sharing. It's like, hey, do you want this electron? Yeah, sure, I'll have it back. And it travels here, and the electron travels here and here, and they're floating around these atoms. Like, if these are the atoms, or really we could even say like the nuclei of these metal atoms. There's the nuclei, okay, that I just drew in there. Electrons are just kind of floating around these nuclei, being passed from one to the other, and that's what a metallic bond is. And that's also why metals are malleable. It's easy to pull them apart because these electrons are not holding on to these electrons, which is holding these atoms together really tightly. So phrasing I've heard is electron sea, or a sea of electrons floating around these atoms. And that would be a metallic bond. Right? There also happen to be an order of strength of bond, where we have ionic bonds are actually the strongest of the three types, and then it goes to covalent, and then our metallic are the weakest of these three bonds. It's the easiest to break. Okay. So those are our three types. Now, reminder, an ionic bond is when a a metal atom, and I know, see, we drew the picture here, and so maybe we can talk about the steps or the ideas. So an ionic bond is when a metal will lose electrons to form a cation, positive cation, and nonmetals gain electrons to form anions, which are negative. And then once those ions are formed, then the attraction between the cation and the anion The attraction between the cation and the anion is the ionic bond. So if we're going back to this idea here of, let's say that this is my metal atom, this is my non-metal, okay? And they go for this tug of war. Well, guess what? This one, low ionization energy, low electronegativity. High ionization energy, high electronegativity. So the non-metal wins the tug of war. So now this guy becomes positive because it lost a negative electron. This one becomes negative because it gained a negative electron. And now this positive thing and this negative thing has an attraction between them. And that's what the ionic bond is. Like we said with covalent bonds, is the two non-metal atoms evolved both have high ionization energy and high electronegativity. So non-metal atoms have the high electronegativity and high ionization energy. Okay? And because they're both strong when they go into that tug of war, they both have a large affinity to trying to take those electrons, and they don't want to lose the electrons. When they go for the tug of war, no one wins the tug of war. So actually, for this next bullet point is going to be a picture. So imagine here's one of my non-metal atoms, and here's the positive nucleus. Okay, and this atom has lots of electrons, but let's just say like here's one of its valence electrons. Okay? And then another non-metal atom, and actually let's draw this attraction. We know that there is an attraction between the nucleus and of the atom and its valence electrons. Now let's say another non-metal atom comes on by. It's not a really pretty circle. And there's its positive nucleus. And guess what? This nucleus has an attraction not only to its own electron, but also to the electron of the other atom. And that this atom not only has an attraction to its own electron, now it's going to try to take the electron from the other atom. But neither one is going to win that battle, and that's what the covalent bond is. Neither one is winning this battle over these valence electrons, and they just end up reluctantly sharing or in a tug of war that no one is actually winning, and that's what's holding them together. When they are equally matched in the tug of war, okay? So equal then we get a non-polar covalent bond. See, it's written little, but non-polar covalent. They're both pulling equally on these electrons. And so that would mean that these electrons are going to spend an equal amount of time over here and over here because the pull is equal. Okay? But sometimes the tug of war is not won, but it's still not quite even. Like, we got a big sibling and a little sibling, but the big sibling's not quite strong enough yet to completely win, but they're definitely a bit stronger than the other one. So this is when they're equally matched, and this is when one atom is a little stronger than the other. And what I mean by a little stronger, like stronger meaning electronegativity, like its ability to pull electrons from other atoms. So the tug of war is not completely won, but the chlorine is stronger than the hydrogen. And so those electrons that they're both pulling on, they are closer to the chlorine. They spend more time over by the chlorine than they do the hydrogen. This is a polar covalent bond. And in a polar covalent bond, we get something called dipoles. Okay. Dipoles mean that there's an area of the molecule that is slightly negative or an area that is slightly positive, but it's not completely negative like an anion or completely positive like a cation, because it didn't completely gain or lose the electrons. It's just the electrons are spending a little bit more time on one side than the other, and they're going to spend their time with the atom that is more electronegative. So if I were to draw a dipole arrow, it would point towards the atom that is more electronegative, and that means the electrons spend more time over here. We would call that the partially negative side. And then the electrons spend less time over here, so this would be the partially positive side. That means the dipole arrow, we give it a little like plus sign on the end, because that's the positive side. Okay. Now, when the battle can be won, when one atom is clearly much stronger or has a much higher electronegativity than the other, then one atom wins the tug of war and one atom loses. Okay, so one atom much stronger than the other. Okay, and again, stronger, I'm meaning electronegativity is a lot higher. And that's when we get an ionic bond. That's when we go for this tug of war, but this guy is so much stronger that he actually wins the electrons. And like we said, now he's negative, this guy's positive, and then we get that electrostatic attraction between the positive and the negative, and that's the ionic bond. Great. So we talked about ionic, we talked about covalent, we talked about when the tug of war is equal, and that would be a non-polar covalent bond. We do not have dipoles here. There's not a side that's slightly positive and a side that's slightly negative. But when one atom is a little bit stronger, but not strong enough to win the tug of war, but a bit stronger, then the electrons will spend more time over there making a partially negative dipole and a little bit less time over here making a partially positive dipole, and that's why it's a polar covalent bond. Metallic bonds are what I was saying, where we have these metal atoms with low ionization energy and low electronegativity. Okay? So great, here's our nuclei of these atoms, right? And these nuclei aren't really holding on to their own electrons all that tightly, and they don't really have much of an affinity to take other electrons. So what happens is these electrons that these atoms have tend to just kind of float around these around all the atoms, being passed from one to the next, in no specific direction. Like there's definitely a direction involved with a polar covalent bond, but it's non-directional in a metallic bond. They're just randomly moving from one to the next. And this is why it's such a weak bond, that imagine there's not a lot holding these guys together, and so it would be kind of easy to pull them apart. And that's why metals bend and they're malleable, because it's easy to pull the atoms apart. Now, as humans, we really, really love to make things fit in a box and to like label them and say, here you are, and this is the label that we give you. So an example of this is when I started off by saying, hey, these are the kind of atoms that are involved in these different kind of bonds. But really, the reason why this happens is not because something is labeled as metal and something is labeled as non-metal. The real reason why those different types of bonds occur is because we get this spectrum of differences in electronegativity. Like if I have a bond between two atoms, like the example that's given here, where it's a chlorine atom and it's bonded to another chlorine atom. And here's those electrons, okay, that they're going to battle over. Well, chlorine has a strength or an electronegativity of 3.16. And guess what? This other chlorine has the exact same strength to them. So if we do the difference in electronegativity, if we subtract the electronegativity from one of the atoms from the other, then that difference here would be 0. If the most purely nonpolar bonds have an electronegativity difference of 0, but we can have a small difference in electronegativity that it's not all that noticeable, and we would still call it nonpolar, and that range seems to be from 0 to 0.4. That's what we traditionally label as a nonpolar covalent bond. But just a heads up, this really is a spectrum. Like, for me to put a boundary on this is such a human thing to do, that we want to say, hey, which side of the line is it on, and what do I call it when it's on that side of the line? So just a heads up, not all scientists agree with that number of 0.4. Okay? It would be better just to make a general comparison, like which bond is more polar, that would be the ones going this way, or which ones are more nonpolar, that would be going this way, or which ones have greater ionic characteristics, that would be going this way. So our next example here is, what about hydrogen bonded to chlorine? Because the strength of hydrogen, it got cut off here. It's a 1.20. That's why there's supposed to be a 1 there. That's the strength of that atom. And chlorine, like we said, was 3.16. Well, if I were to do this difference in electronegativity, where I subtract, and we're always just going to do the bigger one minus the smaller one, because I don't need a negative here. I'm just trying to know what the difference is between them. So if I do my 3.16 minus my 1.2, the difference in electronegativity between these guys is 1.96. So that's a pretty decent difference in their strength. And if that difference, if that difference falls between 0.4 and 1.7, then we like to call that a polar covalent bond. But man, this is that example that I was telling you. Is like, look, it doesn't quite fit into the box. That yes, it's two nonmetals. Hydrogen's a nonmetal, even though it's to the left, and chlorine's a nonmetal. And so we want to call it covalent. We don't want to call it ionic, because it's not a metal and a nonmetal, and these aren't ions. They didn't form ions. But their difference was rather large. And so instead of saying, hey, this is a polar covalent bond, we could say, well, it's more polar than our chlorine and chlorine, or it's less nonpolar. And by the fact that they didn't form ions, I can assume that it's a covalent bond, not an ionic bond. And so this would definitely be on that high end of polar for a polar covalent bond. Now, if this difference, and due to characteristics of the atom, become large enough that they do actually gain and lose electrons, then we would call that an ionic bond. So an example is sodium and chlorine. We do get a bond between sodium and chlorine. Chlorine's electronegativity is 0.93. It's not really strong. It's rather weak. And chlorine, like we said, is 3.16. And if I do the difference in electronegativity here, I get 2.23. Okay? And that's a really big difference in electronegativity, and it's past this line that we like to draw at 1.7, though we just saw it doesn't always work great, where we call this an ionic bond. A better way of thinking about this is, yeah, their difference in electronegativity is really big, but I know that ions are going to form because one was a metal and one was a non-metal. So when you're categorizing something as ionic, I want you to think of, is it a metal and a non-metal, or does it have a polyatomic ion? Then if it's something with a polyatomic ion, it's probably an ionic bond. When it comes to covalent, though, we know that both of these covalent bonds, nonpolar and polar, are between two nonmetal atoms. And I will use that difference in electronegativity to decide which one of them is more polar or which one is more nonpolar. And we can say, okay, if this is that boundary line, then we could call this one nonpolar and that one polar covalent. All right. So let's do one example together and then we'll wrap up this video. It says, which of the following scientific claims about the bond in the molecular HF is most likely to be true? Okay, first thing. We reserve the name molecule for covalent bonds. Covalently bonded things. This means that molecules happen between non-metal atoms. When it's an ionic bond, a metal and a non-metal, we don't call it a molecule. We call it an ionic compound. So they've given me a little hint here. I already know that it's a covalent bond because it said molecule. I also know it's a covalent bond because hydrogen is a non-metal and fluorine is a non-metal. So is this going to be more polar or more non-polar? And I don't have an electronegativity table, but just look at their difference. We know electronegativity is biggest over here. And look at how far away these atoms are from each other. So this one has probably a fairly high electronegativity. This one probably has a fairly low electronegativity. So the difference between them and their electronegativity is probably on the bigger side. So I'm guessing that this is going to be more polar than non-polar. Now let's look at our answer options. So which is most likely to be true? A says there is a partial negative charge on the hydrogen. Okay, fluorine is the bully of the periodic table. It's more electronegative, so that means these electrons are going to spend more time with the fluorine. That would make the fluorine the partially negative side because the electrons spent more time over there, and hydrogen is going to be the partially positive side because the electrons spend less time there. So it's not A. B, electrons are shared equally between the hydrogen and the fluorine. No, they have different electronegativities. They're pretty far away from each other on the periodic table. So I doubt that they're going to be sharing equally. If they were both fluorine, then yeah. The bond is extremely weak. I doubt it. These covalent bonds are fairly strong. They're not as strong as ionic bonds. They're fairly strong, so I wouldn't say that it's extremely weak. And then the last one is the bond is highly polar. Yeah, I bet that's true, especially through process of elimination. And knowing that based on location on the periodic table, where electronegativity is the biggest over here, those are fairly far apart from each other. So their difference in electronegativity is probably fairly large. So that would result in a polar bond. Okay, great. We will get some good practice in during class, and I will see you all soon.